Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows. I am pursuing my PhD from ISR Padhampur in organic chemistry. So I am the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pan from IIT Guwahati. So here in this class I usually discuss about some previous year questions which are based on this topic. Before going to the previous year question, I also try to discuss some concepts to recall your class, and I hope the questions I solve, they are different from your class assignments, so it will help you to fulfill your assignments and also to get broaden your understanding and also the number of questions you solve. So let's start. So in the previous classes I was discussing about the reagents based on silicon, sulfur, phosphorus, etc. So today we will discuss about reagents based on organometallic. So we will discuss about the reagents based on organometallic compounds. So first we will start with the group 1, 2, then we will go to the transition metals. First we will discuss about the group 1, 2 metals, that is I am talking about the periodic table. Then we will go to the transition metal compounds. So first is lithium containing reagents. So this is one of the important kind of reagents. Many of you have heard about butyl lithium reagent. This has been multiple use in laboratory, mainly in organic laboratory. It has, due to its broad application. So organolithium compounds can be generated by the following methods, where this lithium can be added to a organohalide on a alkyl halide compound, and lithium can be replaced with the halogen with the halide compound, generating this organolithium compound. Organolithium compound can be generated by the substitution of sulfide compounds also. So these type of organolithium compounds can be added to in any organic compound and generate this type of can generate a new organolithium complex. So here if you add this organolithium, this butyl lithium into a ketone like this, amide like this specifically take a proton from this ortho position and generate this type of organolithium complex. Similarly in this case also it takes a proton from this ortho position selectively and generates this type of organolithium complex. This this thing can be applied for heterocyclic ring also, and if you add this butyl lithium into a alkenoid complex, where the proton which is more acidic, that proton will be taken up and will give us this type of organolithium complex. This organolithium complex can be generated through halogen exchange with this type of alkynyl bromide, where this bromine has been exchanged by this organolithium complex and generating this species. So here I have shown some of the reactions of this organolithium species. This can be applied for substitution reaction. If you add a selective electrophile into this type of species, it undergoes a after generation of this negative charge here, it undergoes a substitution type of reaction and giving us this as our product. Here it has been seen there is a specifically this SM2 type of reaction where an inversion of configuration has been observed. Suppose you have a group already inside your substrate which is below the plane, then the upcoming electrophile will enter just opposite plane of that one to reduce the steric repulsion. In case of allylic halide, the mechanism is bit different than that of other nucleophilic species. while from the product it seems like it undergoes simple substitution reaction. From the product it seems like that it undergoes simple substitution reaction, but if you go into the mechanism, it has been seen it going through a cyclic mechanism, which has been proved by this type of deuterium labeling experiment, where if you label this proton with a deuterium, it has been seen that there is a replacement of this phenyl group to this center. From this it proves that this reaction is going through a cyclic mechanism, because if it's going through a simple type of mechanism like this happens in case of SN2 type of reaction, there is two type of probability was there. If you mark this proton and reaction is going through a, there is one possibility is this one. One possibility is this one, another is so here, while using organolithium type of species, specifically we are getting this as our product, which proves this reaction going through a concerted mechanism and it's going through a cyclic type of mechanism. This is another reaction of organolithium species. If you add butyl lithium to this type of diiodide species, what will happen? Can anyone guess? As we have said, this halogen undergoes a lithium halogen exchange, so this will attack here and generate a carbonyl center. Organolithium species. Now it undergoes simple nucleophilic substitution, generating a 6,4 fused cyclic ring. Okay, let's go to the next topic, where it contains magnesium containing reagent. So next we will discuss about, so magnesium belongs to group 2. Magnesium belongs to group 2. So magnesium containing reagent, the one of the very renowned, or everyone have heard about this one, that is Grignard reagent. So organometallic compounds like this RMGX are called Grignard reagent, after the French chemist Grignard got a Nobel Prize for that in 1912. So this type of Grignard reagent contains a metal, that is this magnesium inside it, and a halogen species. Where this halogen, this metal is less electronegative than that of specifically the R group, because this belongs to the left hand side of that. so it belongs to the left hand side of that group. So because of that, this magnesium is more electropositive than that of carbon. So so it contains a delta positive charge, and it shifts the electron density towards the carbon. So the carbon becomes a delta negative charge, and this is how this carbon becomes a nucleophilic carbon. In this way it can be prepared. While in organic halide, if you add magnesium and diethyl ether, it will form this RMGBr, that is the Grignard reagent. And so there are some examples of Grignard reagent. So this can be used for preparation of ketone, aldehydes, esters, acids also. So if you add this Grignard into a acyl halide, it will attack at this place and remove the fluorine from the system, generating this ketone. While if you add this RMGX into this acetonitrile complex, it will attack to this carbon center and it will break one of the triple bond and form this type of complex. After addition of water, this MgX will be removed and give us proton to form this ketamine type of compound. After into that, another molecule of water will attack and through elimination of proton we will get this type of ketone complex. In this way you can also prepare a aldehyde. If you add this Grignard to this type of species where this amide can be used as a leaving group, this can generate an aldehyde. Similarly, if you add this type of ether type of complex to eliminate, it will eliminate it will take one of the ether group. It will take one of the ether group and generating a positive charge. Then RMGX will R center will attack to this positive center. After, if you add water, this is the acetal type of system. So I have already talked about this acetal preparation in one of my videos. It undergoes a deprotection and it will generate aldehyde as our product. So this Grignard reagent can also be reacted with epoxide. If you add Grignard to a epoxide, it will attack to the less hindered side. It will attack to the less hindered side and generate this type of alcohol as our product. There's another example. If you add RMGX to carbon dioxide, this carbon is electrophilic because of 2 oxygen atom. So this R nucleophile will attack to this carbon center and this will open up. By this method we can insert acid group in the complex. Okay. In the case of unhindered cyclohexane with Grignard reagent, generally there is a preference for attack from the equatorial direction to give an axial product as the major product. So if you add this Grignard reagent to the cyclohexanone type, it specifically attack to form this equatorial position, giving us this axial alcohol as a major product. So for cyclohexanone, if you are adding Grignard, it will specifically attack from the equatorial position which is a less hindered position, and generating a axial alcohol. This is another reaction of Grignard, where this type of allylic Grignard reagent undergoes this type of rearrangement, where this Grignard, this delta negative carbon center can be replaced to this position. Because of that, if you add this allylic Grignard reagent into a ketone, instead of this carbon position, instead of this nucleophilic center, it attacks through this allylic position because of stability of this cyclic transition state, and giving us this as our product. Similar case happens in case of phenyl magnesium bromide, where this attacks through its allylic position, that is the ortho position, instead of the simple aliphatic carbon, because of the cyclic transition state, which attains the stability and giving us this ortho product instead of a product from the CH2 position. So this does not form. If we would attack from the CH2 position, it would give this as our product. Okay, it happens the driving force of this rearrangement is the stable driving force of this reaction is stable cyclic transition state. Okay, so if you compare the Grignard reagent with the lithium compounds, suppose you are given this alpha beta unsaturated type of ketone, and you are adding this Grignard reagent and a lithium compound, what will be the selectivity? Because this type of compounds has two electrophile, one is this one electrophilic center, another is this one. Now which will react? So in case of Grignard reagent, it specifically react with this beta carbon, giving us this as our product. Whereas in case of lithium, it attacks to this carbonyl center, it attacks to the carbonyl center, giving us this alcoholic species. Okay, let's go to the next question. So how will you prepare these two compounds from in 1 and 2? So this ketone has been given. How will you prepare this epoxide, and how from this aldehyde how will you prepare this epoxide? So this can be prepared in various steps. I am showing one of them. So if you just add this type of silyl ether we add this type of species, silicon, we have already talked about silicon, so this is one of the example of that. If we add this type of silicon species, what will happen? They will generate a negative charge and it will attack to this carbonyl center. Generating this type of stereoselectivity complex. After that, if this O minus attack to this electrophilic center, it's getting complicated. It will form this epoxide. So if you add a Wittig reagent, a specific Wittig reagent like this, PPH3, CH2, CH3. This can be prepared from ethyl bromide. This can be prepared from ethyl bromide and PPH3. Yes, this can be prepared from ethyl bromide and PPH3. What will happen? So this will attack to this carbon center will attack to this carbonyl center, and it undergoes a alkylation and form this type of alkene. After that, if you add MCPPA, it forms this epoxide as our product. In the similar way, if you add PPH3, CH2, it will form this alkene, and if it undergoes epoxidation with MCPP, it will form this epoxide as our product. Let's go to the next question. So suppose in this type of aromatic species butyl lithium is added. So from the species you can see that okay, there is a one proton will be abstracted by using butyl lithium. Now which proton will be abstracted? There are three protons are there. One is this one. These two are equivalent, so there are two types of protons are there. So which will be abstracted by butyl lithium? So as this is just adjacent to two electron withdrawing group, so this hydrogen is highly acidic. This hydrogen become highly acidic. This hydrogen become highly acidic. Because of that, butyl lithium will take up this proton and generate an organolithium species here in this space. And when you add this type of alkynyl bromide, this center will attack to this carbon and it will generate this as the substituted product. Generate this type of substituted product. When we add butyl lithium to this type of bromine complex, bromohalide, what will happen? This will attack to this bromine and will generate this type of, because we know that alkyl bromide organolithium complex can be generated by using this halogen exchange. So this species will attack to this carbonyl center, will open up, and as our product we will get acid. There will be a carbonyl species. C. Okay, understood? Next is this one. So what will happen if you add this phenyl lithium to this 2-methyl pyridine? Now from this species you have seen that okay, the proton has been abstracted from the aromatic proton. Now there is an option of aliphatic proton also. So as the pyridine ring are highly, if there is a sp3 carbon available just attached directly to the ring, then there is a probability of taking this sp3 proton instead of this aromatic proton. So whenever there is a sp3 hydrogens are there attached to directly to the ring, this will not be taken because these protons are not directly attached to the ring, whereas here this methyl group is directly attached to the ring. So proton will be abstracted from this CH3 and organolithium species will be generated here. Will be generated here. after that, if it attack to this aldehyde, it forms this alcohol as our product. Okay, let's go to the next question. So next topic we'll discuss about, so this group 1 2 has been completed. Now we'll move to the organometallic reagents of transition metals, organometallic reagents containing transition metals. So today we will discuss about the zinc complexes. In the next class we will discuss about the most important metal in organometallic chemistry, that is called palladium. So there are huge number of reactions which are based on palladium. In the next class we will try to discuss about palladium reagents. So if you add ketone, if you add this alkyl bromide into this zinc type of species, it will form this organozinc complex. Because of that, this center become highly nucleophilic, and then this can attack to this carbonyl species and react to give us this type of alcohol as our product. Similarly, in this case, the same thing will happen. Zinc will enter to this carbon halogen bond, and after that this nucleophilic species will attack to this carbonyl compound, forming this alcohol as our product. In this case also, what will happen if you add zinc to this halogen complex? It will form this species. After that, if you add this type of aldehyde into that, if we add this type of aldehyde into that, this negative center will attack to this carbonyl compound, it will open up, forming this alcohol species. After that, if you add H plus into this, it undergoes protonation, and through water elimination it forms this alkene as our product. Understood? Let's go to the next question. So here I have shown one of the practice set based on lithium and magnesium containing reagents. So let's solve one by one. Because of first of all, I just give 1 minute, just try. How many of you can try to get the answer of most of the question I will Then after 1 minute I will solve one by one. Just give it a shot. Most of the I have already solved questions based on this type of questions. So I hope whatever I have solved till now, you can take those as a reference and try to attempt this. So let's solve one by one. If you add butyl lithium in this type of brominated species, what will happen? Alkyl bromide, this bromine will take up by this butyl lithium, and when you add this aldehyde, it will form this alcohol as our product. Okay. Next is this one. If you add this Grignard reagent into this acetonityl complex, what will happen? This delta negative will attack to this carbon center and it will open up, forming I'm just showing the cyclohexane, this imine type of complex. Okay, as there is no water is given, if water is given it will turn into aldehyde. As there no water is given, because of that it will remain as this imine product. Next is this one, this type of problem we just solved. They just change the group here. So what will happen in this case? This butyl lithium will take a proton from this position and this allylic bromide will enter and we will get, I am not drawing the other part of the product. So all other species will be same. It will just attack to this center, giving us this as our product. Okay, the other part will be as same as the substrate. Other part will be as same as the substrate. Only this center will react. Okay. In the next question, if ETMGBr is added to this type of alkyne type of species, so we know this type of hydrogens are highly acidic. These alkynyl hydrogens are highly acidic because they are sp hybridized, and sp carbons are due to high s character they are highly electronegative, which enhance the acidity of this proton. So this ETMGBr will take a proton from this position, generating a negative charge here, and this negative charge will attack to this carbon center, removing this bromine from the species compound. So it will generate this type of dialkyne species. Okay, understood? Next is this one. If you add methyl lithium into this complex, what will happen? So first, so this will attack. So what will happen to this one? Okay, I am just giving this. It is quite different. I am giving this as a homework. Just try. I will solve this with you in the next class. I am giving this as a homework. Just try. What will happen in this case? This is similar to the whatever we have solved. So this will just attack and will give us this 6,4 fused cyclic ring. Okay. This was I am also giving as a homework. Just try. We will solve it in the next class. So let's solve some. There are some previous year question. It came in GATE 2023. So what will be the answer of this one? I just give 10 seconds. Just try. So if you add this is called Gilman reagent. So if you add this Gilman reagent, it will attack to this selectivity to the beta position, and a negative charge will generate here, and it will attack to this selenium complex, and bromine will be removed. So it will generate this as our P. So in the next step, if H2O2 is there, this selenium will be oxidized, and in presence of it will take a proton from this position, and it undergoes the elimination, giving us this as our product. So the correct option will be option B. This is also a question from GATE 2023. What will be the product of this one? So the time is Grignard reagent is added, so it will attack to this aldehyde species and it will open up, and H plus is there, so it will be protonated, generating this as our species. Now in the next step, if H plus is as H plus is still in the medium, so this alcohol will be protonated again and removed from the system, generating a carbocationic species. Now this is 2 degree, not that much stable, and with a 4-member ring with huge strength, to get some stability, this bond will shift, which will form this five-member ring. Next, it becomes a 2 degree with a 5-member ring, 2 degree with a 5-member ring. This another probability is this: there is a proton here. This proton can be shifted to this carbocation center, generating this cyclopentane with the positive center at this position. This becomes a 3 degree with the 5-member ring, which is more stable. 3 degree with the 5-member ring, which is more stable. And as in the medium already Cl minus is there from the HCl, so this Cl minus will attack to this carbocationic species, generating this as our product. Okay, let's go to the next question. In the following reaction, the stereochemistry of the major product is predicted by, so here they have shown that this will be the major product. So what rule has been followed in this case? So usually this type of organolithium type of species always follows this Cram's rule. Now here there is a group OMe3 which undergoes a chelation with this carbonyl species. Because of that, the reaction will go through a Cram's chelation model. Because of that, the reaction will go through a Cram chelation model. Reaction will go through a Cram chelation. Because of presence of this OMe group, there will be a formation. There will be a chance of chelation in this place. So this is going through a Cram chelation model. Okay. What will be the product of this one? So if you add butyl lithium, so this it will take a proton. These allylic protons are highly acidic. Now both the centers are allylic. This is a allylic position, this is a benzylic position. Which one will react? Obviously the benzylic positions are highly acidic. This is more acidic. So butyl lithium will take a proton from this position. Then it will undergo this type of rearrangement where so the correct option will be option 2. So the correct option will be option 2. Okay. So what will be the major product? So here now we will solve some questions of which are based on the topics we have discussed in the last few classes. But whenever I am getting some important questions which are based on those topics which we have already discussed, I am trying to include them. So let's try to solve this one. After that I will solve it with you. I am just giving 10 seconds. Just try to solve this one. you know that if MCPB is given to a double bond, what will happen? It will generate a epoxide. So the A will be obviously a epoxide. A is obviously a epoxide. Now there are two kinds of product. One is acid catalyzed, another is base catalyzed. Not base catalyzed. One is so okay. This sodium methoxide is a base, whereas this HCl is an acid. So there is this ring opening. One is base catalyzed. One is base catalyzed. Another is acid catalyzed. Because of that, the ring opening mechanism will be bit different. So when the reaction is base catalyzed, this base will prefer to attack to the less hindered side. The base will prefer to attack to the less hindered side. So the base will attack to this less hindered side. So the product will be this one in case of base. So this is our B in case of base. Now when this reaction is acid catalyzed, this center will be protonated first. The oxygen will be protonated. After that, it undergoes a ring cleavage, which generates a carbocation at this center. Now why not the ring cleavage is happening from this position? Because you can see after the ring cleavage, here it is generating a 3-degree carbocation. But if the ring cleavage was happening from this position, it would generate a product like carbocation center at this, which is 2 degree. Because of that, this ring cleavage will not happen, and after the addition of methanol, here, it will give this as our product. So the correct option will be option 3. So the correct option is not option 3. So the correct option is option 4. So this is our B, this is our C. Okay, the correct option is option 4. Let's go to the next question. So what will be the major product formed in the following reaction? In the last class, when we were discussing about silicon, we have told if you add iodine to a silylated species, what will happen? It will just replace the carbon silicon bond with a carbon halogen bond. It will just replace the carbon silicon bond with a carbon halogen bond. So the stereochemistry will be intact. So if you just iodine will be added, so it will give us this as our product. There are no stereochemistry will be hampered. So this will not be formed, not even this one. So only specifically we will get this as our product. Only the carbon silicon bond will be replaced by the carbon halogen bond. We have discussed about this topic. You can go and check in the last video. Here we have discussed about this. So what will be the major product of the following reaction sequence? This is also a question from NET 2024. So in the first step, they have given acid. So obviously this OH will be protonated. And get removed from the system. This OH will be protonated and get removed from the system, generating a carbocation species. Now, as this is 2 degree, not that much stable, so this methyl will shift to this position. Form this dimethylated species with the carbocation center here. Now there is a proton at this place which can be eliminated to give us this alkene. Now if you add osmium tetroxide NiI4 and tertiary butox, so osmium tetroxide will undergo a dihydroxylation of this complex. In presence of NaIO4, it undergoes a ring cleavage. If you want to know about the mechanism, you can ask me. I will try to discuss it in the next class. For now, I am not discussing about the mechanism. So whenever NaIO4 is added to a dihydroxy compound, it undergoes a ring cleavage and there will be 2 carbonyl center. Okay, so the correct option will be option 3. Let's go to the next question. So what will be the major product formed in the following reaction? So this one also I have discussed in the earlier classes. If BO3SNH is added, AIBN is added to a iodo species, what will happen? So this will take this iodo and it will generate a radical center here. So it will just take this iodine, carbon iodine bond and it will generate a radical species here. So the radical undergoes a insertion reaction to this carbon. So it can attack to this center, it may attack to this center also. So which is more preferable? So it has been seen that 5-exo trig are more favorable. 5-exo trig are more favorable. This is from the Baldwin's rule. If you want to know about that, you can. I will try to discuss this in the next class. This is from Baldwin's rule. So 5-exo trigs are more favorable. Because of that, it will form this type of 5-member ring. Now the question is, here there are two types of 5-member ring. One is this one, another is this one. So that you have to see the difference. Here both the hydrogens are seen to each other, here trans to each other. So what will form? So obviously during insertion reaction, the newly formed ring try to be in the same plane to avoid this stain. So because of that, if this is above the plane, so suppose if this is below the plane, this total thing is below the plane, so it has to form this ring in a feasibly, so it has to approach from the below the plane. So these two bond will form at the below the plane. Similar in consequence, these two hydrogen go to the same plane that is above the plane. So the correct option will be option B, not D. Okay. Let's go to the next question. So this was one of the homework I have given in the last class. What will be the product of this one? So if you add lithium liquid ammonia, an acid is given, what it will form? As acid is given, so it will form this type of species. Now in presence of NH4Cl, this center will be protonated. NH4Cl contains a slight amount of HCl. Because of that, this will be protonated. So because of that, this can come here and get removed from the system. Then again this lithium will attach to this plane. This goes here, forming this as our product. correct option is option 1. So this much for today's class. I will just give an overview of. So first we discuss about we started with discussing about the organometallic reagents of group 1 and 2. First we discuss about lithium containing reagent, where we have discussed how lithium organolithium species can be generated by different processes and their reaction procedure. Then we discuss about some examples of that one. Then we move to Grignard reagents and their reactions and examples. Then we compared the reactivity of regioselectivity of Grignard and lithium compounds. Then we tried to solve some practice questions. Then we discuss a bit about zinc organocomplexes. Then we move to solving some previous year questions from GATE and NET. In the next class, I will try to discuss more about the transition metal containing reagents like the zinc, palladium, nickel, iron, and there are huge application of that also in our industry and in our laboratory works. So I hope this will be helpful for you. So thank you everyone for attending my class. We'll meet in the next class at the same time. Have a nice day.